Today in physics, we want to talk about the wave behavior, both in longitudinal waves and transverse waves. We're going to talk about what happens when a wave meets another wave or when a wave meets a barrier. And so we want to learn a couple of different terms. We're going to talk about the terms reflection, refraction, and diffraction. And we want to be able to kind of distinguish when does a wave do these different things. So when a wave reaches a barrier, some of that wave could bounce back and return to its original medium. You noticed that happened when you did the Slinky lab and sent a wave to your partner. It hit a rigid barrier, it hit a fixed end when it hit your partner's hand. Well, it bounced back and came back into the original medium. Now for that lab, the medium was the Slinky itself. It is possible also that some of the wave might be passing through into the next medium, which is the case when light waves from the sun strike a window, and then those light waves continue to travel into the room, and you can see, we can't see those waves, but we know that those waves come through that object, otherwise we wouldn't be able to see outside. So how much reflection there is or how much refraction there is depends on what we call the rigidity of the medium, and in terms of how firm does that wave perceive the medium to be. So rigidity depends on the material, but it also depends on the wave that's hitting it. Okay? So there's several things that affect the speed of a wave through a medium, but the most important thing is the speed of a wave is determined by the medium itself. Whatever the wave is going through, that's what determines the speed of a wave. My voice is going through air, so the speed of sound depends on the air. You shake the Slinky and it went through the coils, and so the wave speed depended on the Slinky. If you had a different kind of Slinky, it would change the speed. You can throw a rock in the water and the particles go up and down, and the speed of that wave depends on the water. So the speed of a wave always depends on what the wave is going through. It does not change by changing the amplitude or changing the frequency. That does not change the speed. It does change other things about the wave, but it does not change the speed. So when we talk about the different types of medium, in air, temperature affects the speed. If the air is warmer, it has more kinetic energy, and so the speed of the wave is faster. In water, depth affects the speed. So waves that are into the deeper part of the ocean travel a different speed than waves when they come crashing onto the shore and the water gets more shallow. That changes the speed. In solids, rigidity affects the speed. So the speed of a wave in a baseball bat from the time that the ball hits the bat until it reaches your hand is different than the speed of a wave through metal. So waves that strike a boundary can either be returned to their original medium, that's a reflection, or they can pass through to the next medium, and that's a transmission. An incoming wave, we've already talked about how an incoming wave is called the incident wave, and then the wave that returns is called the reflected wave, or if it goes through, it would be the transmitted wave. If a wave comes and hits a medium and it goes through, most likely that phase or that pulse will stay upright. You notice that when you shook the Slinky, when it hit your partner, it returned and it flipped over. So that's a wave that would hit a barrier and be reflected, and so that can be inverted. And then reflected waves can lose their amplitude, and they can transfer energy to the barrier, and they can transfer energy to the medium itself. And you notice that as you shook a wave, the amplitude changed as it came back, even as it traveled along the Slinky. It's important to note that even though that happens, the speed of the wave does not change. And then we have this principle of superposition. You and I cannot superimpose. Matter cannot be in the same space at the same time. If you have a bucket full of water and you take a rock and you drop it in the bucket, the rock displaces an equal volume of water. You and I would do the same thing. We would push another object out of the way. But waves are energy, and so because they can be in the same space at the same time, we say they superimpose. It turns out that when they do superimpose, as they bring their amplitude with them, remember that's the energy of the wave, those amplitudes will algebraically add together. And so that can cause the wave, the amplitude of the wave to be bigger, or it can cause it to be smaller. If that wave is built up and it's bigger, that's called constructive interference. And if that wave gets smaller, that's called destructive interference. So here's a couple pictures of some constructive and destructive interference. So you can take a look at these a little closer. You have a blue wave and an orange wave, and as they interact with each other, if they line up in phase with each other, that means a crest of one wave meets a crest of another wave, or a trough of one wave meets a trough of another wave. These waves are in phase, and they create this bigger amplitude of waves. They also produce these places where you have no displacement, and those are called nodes. So we would have nodes at each point where it crosses the equilibrium position. You can see those better when you've got a little bit of destructive interference. But so you can see that the nodes here and the nodes here, these are places where one wave has crossed another wave and their amplitudes have canceled. When you get that just the right frequency where the incoming wave and the reflected wave interfere and they produce those nodes, you get a standing wave. And a standing wave is simply, you know, if I send a single pulse on the slinky, you can see the pulse move from me down the slinky. It moves from one place to another. A standing wave is still oscillating, but it looks like it's not moving from one place to another. It looks like it's oscillating but staying put. And then this is a standing wave generator that you can take a look at, a link to both of those. So when we study waves, we want to predict some behavior, figure out what's this wave going to do or where is the wave going to be. And by doing that, we want to draw a model. The model that we draw is called a ray diagram. So we treat a wave or a group of waves as we draw a line perpendicular to them to represent a ray of energy coming out of something and hitting something. So, you know, the sun, this big, huge ball of fire in the sky, emits energy in all directions, in 3 dimensions of space. And you can kind of think it like in 2 dimensions, like if you throw a rock in the water and you see rings go out in all directions. Our sun is doing that same thing, sending rings in all directions. But we do not recognize this as, oh, hey, that's the sun. Instead, we draw rays coming off of the object that we have drawn them. We draw a line perpendicular to those wave fronts that are coming out. So we draw a picture of the sun and we're like, oh, that is the sun. That's what the sun looks like. These lines that are coming out are rays of energy. And so a ray is perpendicular to those wave fronts that would have come here like this. As this ray comes toward the earth and it's going to strike the earth, here's the surface of the earth. When a ray comes in and strikes the surface, and these things travel in straight lines, we draw a line perpendicular to the surface. That is called the normal. It's just a line perpendicular to the surface. And we measure the angle between the ray and the normal, never between the angle and the surface. So we measure this angle of it coming in. We call that theta I, the angle of incidence. And this ray, if it comes in and strikes the surface and then it's going to be reflected out, it will follow the law of reflection and it's going to bounce back out at an equal angle. So we say the angle of reflection, theta R, is equal to the angle of incidence. Theta I equals theta R. This is the law of reflection. Every wave follows this law. Even when the surface is bumpy and not smooth, every individual wave still follows this law. And all types of waves, okay, waves of light, water waves, all of these things follow this law of reflection. So this top diagram is a picture of the law of reflection, and we have the wave fronts, and then we draw a line perpendicular to those to represent the ray. And then they measure theta I, once again, between the ray and the normal. and theta r, the reflected ray, comes off the surface at the same angle. But when waves go through a material from one medium into a different medium, because of those different mediums, the wave itself will change speed. Remember, speed is determined by medium. So here's an image of a ray coming in and striking a surface, and we've drawn the normal, and we have an angle that it came in at. And then when it's in this other surface, it changes direction. And this wave will either speed up or slow down based on the new medium. If the new medium is more dense, it's going to slow down. If it's less dense, it's going to speed up. So when sun's rays come from air to water, water is more dense, and so the ray moves more slowly in the water. Well, when something slows down, the wave will bend toward the normal, and when something speeds up, it will bend away from the normal. And that's really all that you need to know. What's important about this is bending of a wave because it changed medium, and that is called refraction. Bending of a wave because it changes medium. This is why if you stand in a swimming pool and you're using light from the air and then you look down at your feet, especially if you're waist deep in a pool, your feet are going to look like they're kind of disproportionate to your body. They're going to look like they might be a little closer to the surface than they really are. And this is also why we tell you don't dive into water if you don't know how deep it is, because it's going to look like it might look like it's much deeper than it is, but it might be very, very shallow. What something looks like has to do with the way light is behaving in that medium. So we want to be careful with that, how that works. And then the last type of bending happens when wave bends around a barrier, but it's not changing medium. So that is called diffraction, the bending of a wave because it's either going around a corner or it's going through an opening. And here you can see we have some straight wave fronts. There's a ray coming through. It hits this small opening and then it comes out kind of curved because some of the wave lags behind. And that is called diffraction. So we have two different bending. We have refraction and diffraction. Refraction happens because I change speed, which means I change medium. Diffraction, I'm staying in the same medium, but I'm bending around a barrier. So you can see this happen in the water when a water wave comes and it strikes a group of rocks or an island. And the wave itself will bend as it goes around that barrier. Since it's not changing medium, that is diffraction. So there are several videos that you can take a look at, and I'm going to do some demonstrations for you a little later on, and I'll post that to Canvas for you too, so that you can see those demos and try to represent interference, standing waves, and possibly some refraction.